Now we're going to take a look at similar right triangles. So we're going to look at the altitude to the hypotenuse of a right triangle, and we're going to see how it divides that right triangle into two more right triangles that are each similar to the original right triangle. And we're going to define and apply what a geometric mean is. And then we're going to try to calculate the lengths inside of related segments for those right triangles that are created. And we're going to use proportions to do that. So the first theorem that we need to know is that if we have an altitude that's drawn from the right angle to the hypotenuse of a right triangle, it's going to separate that triangle into two smaller similar triangles, each of which is similar to the original triangle. So here's an example of that. So notice that we had triangle ABC, and we drew an altitude from the right angle to the hypotenuse. So remember, an altitude has to have a right angle right there. And then what we did is we created two smaller triangles. So we have triangle ADB, and we have triangle CBD. And then those two smaller triangles, ADB, is congruent to that big triangle, ABC. And then also that this other triangle, this BDC, is congruent to the big triangle, ABC. And then therefore, using the transitive property, we do know that that first triangle that we mentioned, that ADB, is congruent to this other triangle that's created, that BDC. In the proportion A over X equals X over B, you'll see that the denominator in this first ratio is the same as the numerator in this ratio. Whenever this happens, whenever this occurs, where the denominator is the same as the numerator in a proportion, we call that number that appears in the numerator and the denominator, it has a special name. We call it the geometric mean. So for example, in this ratio, 8 would be the geometric mean of 16 and 4 because if you look at this ratio, 16 over 8 equals 8 over 4. So 8 is the denominator here, but the numerator here. So let's say we want to find the geometric mean between 3 and 27. So to find that, we would say 3 over x equals x over 27 because it has to be the denominator in this ratio, but the numerator in this ratio. So if you think about fractions, 3 over what equals what over 27? So to solve that, we can cross multiply. So x squared is equal to 3 times 27, which is 81. We can square root both sides. So we get plus or minus the square root of 81. The square root of 81 is 9. We're not going to have negative 9. We're just going to do positive 9 because we're typically talking about distance, and distance cannot be negative. So we'll just say that x is equal to 9. So the geometric mean between 3 and 27 is equal to 9, which makes sense because 3 over 9, which is 1/3, is equal to 9 over 27, which is 1/3. Let's do another geometric mean. We're going to do the geometric mean between 6 and 9. So remember, it has to be the denominator in this ratio and the numerator in this ratio. So 6 over x equals x over 9. So we'll cross multiply. X squared is equal to 54 because 9 times 6 is 54. We square root both sides. So the square root of 54 is not a perfect square, so all we can do is simplify it. So 54 breaks down into 2 and 26, and then 2 and, it breaks down into 2 and 27. So 2 and 27, and then 27 breaks down to 9 and 3, and 9 breaks down into 3 and 3. So we can pull a 3 out, and leaving us a 6 on the inside. So x is equal to 3 roots of the square root of 6. And we're going to go ahead and drop the negative from taking the square root because distance will always be positive. So let's find the geometric mean between 5 and 25. So 5 over x equals x over 25. So x squared is equal to 125. So whenever we take the square root of 125, it's not a perfect square, which means that we have to simplify it. So we can pull a 5 out, leaving us a 5 in the root. So x is equal to 5 square root of 5. If you were to check that on your calculator, you should get about 11.2. However, we don't want to put 11.2. We want to go ahead and write it as accurate as possible, which would be 5 square roots of 5. Next theorem we want to look at is that in a right triangle, the altitude to the hypotenuse cuts the hypotenuse into 2 segments, and that the length of the altitude is the geometric mean between the lengths of the 2 segments of the hypotenuse. So we can use the length of the altitude, and that is going to be the geometric mean. For example, here is this triangle that we have. So it's triangle ADC, right? So here's our triangle ADC, and here's our altitude that we drew between D and B. So here's our altitude. So this altitude has a length of x, and that length is going to be the geometric mean between the 2 sides of the triangles that are created. So it's going to be this side A, right, and this side B of this triangle here. So that means A, so this side of the smaller triangle, over the geometric mean of x is equal to x, which is the geometric mean, over the side of the other triangle, B. Okay, you can also, instead of using the little letters, okay, you can use the names of the segments. So this segment of this triangle, which is segment AB, over that altitude or that geometric mean, which is segment DB, is equal to that geometric DB over the side of the other triangle, which is side BC. So knowing these proportions can help us solve for sides that are unknown. Our next theorem that we want to look at is that in a right triangle, the altitude to the hypotenuse divides the hypotenuse into 2 segments, such that the length of a leg is the geometric mean between the hypotenuse and the segment of the hypotenuse adjacent to that leg. So, for example, AB, which is the leg of this triangle, over AD, which is the hypotenuse of that triangle, is equal to AD again, because that hypotenuse is our geometric mean, over AC, which is the leg of the big triangle. So using that same theorem but the other sides, we can also say BC, which is the leg of this triangle, over DC, which is the hypotenuse of that triangle, is equal to DC, which is our geometric mean for this theorem, over AC, which is the hypotenuse of the big triangle. So we can apply this theorem now using this example. Let's say that we want to find these sides. We need to find a side X, side Y, and side Z. So the very first thing that we're going to do is set up our proportion. So we can use our theorem that the leg of this little small triangle over the altitude is equal to the altitude over the leg of the other triangle. So we have 4 over x equals x over 16. We'll cross multiply, and when we cross multiply, we get x squared is equal to 64. We square root both sides, and we get x equals 8. So now we know what this side is. We now know what x is. So now we can solve another side. Let's solve for side y. So that one is a hypotenuse. So we're going to use the fact that the leg of this small triangle, 4, over the hypotenuse of that small triangle, y, has to be equal to that hypotenuse y over the hypotenuse of the big triangle, which is 16 plus 4, which is 20. Now that we have our proportions set up that we used our theorem for, we can cross multiply, and we get y squared equals 80, and we have to square root both sides. And when we square root 80, that is not a perfect square, and since it is not a perfect square, all we can do is simplify it. So 80 is the same as saying 16 times 5, and when we do 16 times 5, the square root of 16 is 4, so our answer becomes 4 square roots of 5, and that is the length of y. Now we can solve for side z. So side z is the leg of the big triangle. And so to find the leg of the big triangle, we can use the fact that, actually it's also the, hypotenuse, sorry, it's this leg right here, but it's also the hypotenuse of this small triangle. If you see how this is the hypotenuse right here, so we can use our hypotenuse theorem. So we can use the fact that this leg, 16, over the hypotenuse of that small triangle has to be equal to the hypotenuse of the small triangle over the hypotenuse of the big triangle, which is 20. So we cross multiply, and we get z squared is equal to 320. And then we square root both sides. And when we square root both sides, 320 is not a perfect square, but it does simplify to 64 times 5, and the square root of 64 is 8. So our answer becomes 8 square roots of 5 as our final answer.